Okay, so this is a school microscope, very nice microscope. It's several $100s. This one was about $450. This is the open flexure microscope, and it's widely used. It's an open source microscope that's 3D printed. It has a Raspberry Pi in it. It has a custom motor control board that controls several stepper motors. And it's widely used in university research laboratories for two reasons. One, you can get capabilities that rival those of a $5,000 research microscope for probably $500 or less. However, one thing about using this in a school is A, it's complicated, and B, its functions are opaque. There's a shroud on it, so you can't really see what's going on. Go ahead and share our screen in a minute. Give me just one more, since I'm doing this. So we talked with the folks in London, or who are now at Scotland, University of Edinburgh. And we said, have you ever thought about doing a version for schools? And they said, yes, we did. We got a grant to do just that just before the pandemic. And then the pandemic happened. We couldn't get out into schools. And so we spent the money on something else. And I said, but they said, we'd be happy to support you in developing one. So this microscope over here is the SNAP microscope. It's our version. It's simpler to assemble. We're going to share a screen at this point. And no, where's our? It's right. No, I want the Uganda slides. And and we're working with this is a school in Uganda. The annual this is in the Eastern District of Uganda, near in Baduda, just on the edge of Lake Victoria. The average annual salary is $200 a year. So that means the school microscope that I have on the table would be the equivalent of 2 years' salary, which means there aren't any microscopes in any of the schools in that area, not a single microscope. They just look at pictures of microscopes in books. So we sent a Bamboo A1 Mini 3D printer to this school, and they used that printer to print out a copy of the same microscope that you see on the table. And so now they're not only having microscopes for their science classes, but they're starting to make microscopes for other schools in the region. So that's sort of the motivating factor. Now, if we go back to SNAP, the SNAP comes into it because this is the slide. And I want to give a shout out to all of the people that developed the bridge between MicroBlocks and SNAP. And I also want to say the version 10 update has been fabulous, because that's really what enables us to do it. We have the SNAP bridge, which connects us to MicroBlocks. And then if we go over to MicroBlocks, you can see if we, can you show the rotation with the, so we do micro steps for the stepper motor that's attached to the focus knob. You can make the microscope just manually focused, but then the next phase is to create a microscope that can be controlled by SNAP. So if we go back, one of the things that is wonderful about SNAP is the pixels library. And so if I download the pixels library, then in the pixels library, we get, I think you got it. It just comes up in looks or something. No, I didn't. I didn't actually. Okay, so now that we've got the pixels library, we've got all these wonderful filters that are just built into Snap. And so if you kind of look at what's inside the filter, you can have a Gaussian filter, for example. And then if you look a little further down into what's actually driving this, there are a series of tables that they call, what do they call
Kernels.
What?
Kernels.
They call kernels. They're these matrices, and there's a bunch of them. And you can actually have kids, you know, bring in Alonzo or some other costume and blur or sharpen them and see how it works firsthand. Once they learn how that works in Snap, then you can use this same filter to create an autofocusing program. So you can then, you'll recognize this is the same matrix. And so what you're doing is basically saying, if it looks blurrier, then you need to turn the knob one way. And if it's getting sharper, you need to keep going until you go too far, and then you back up. So there are a number of open source programs that already do this, but they're opaque. They're not, if you have a seventh grader, there's very little chance that the seventh grader or the eighth grader could understand how it works. But here, they've got access to the software. One of the things that we're working on right now is building an API to connect to iNaturalist, which currently has over 3 million images that citizen scientists have contributed. However, here's a remarkable fact. More than 5,000 peer-reviewed scientific papers have been published since 2008 using the images in the iNaturalist library. Almost none of them are from the tropical regions of the planet, even though that's one of the greatest sources of biodiversity. And so by equipping kids in Uganda with microscopes, they will be able to eventually upload images, and we'll start getting more contributions from that region of the world to these larger databases. Then we're working with Rich Glen, who is a professor who teaches the machine learning courses at the University of Virginia. The TA for his course, Matthew, this fall is going to start working on routines to allow the kids to work on automated classification systems to automatically classify the sites they identify. And so we've got kids in the US and kids in Uganda. Maybe we'll get kids in Germany at some point. And our goal is for them to be able to capture slides, capture images, and share them across biomes and regions. But I think what makes all this work, you know, last night I was reflecting on Brian Harvey's talk, his keynote for his ACM award, which was obviously well-deserved. And he said his greatest contribution was the Computer User Society. But I think I would add to that list the community that Jens and Dan Garcia and Brian and everyone else has created on the Snap forum, where almost anything you can think of, you can post a question or ask for insights and get people helping you, usually within a few hours. And so as we were developing these routines, we posted them on we really weren't sure how to go about this. But if you go back in the Snap forums, you'll find the threads where you're asking people about this. And eventually we got to a resolution. So we wanted to get just far enough of you for you to see, but before I want to leave a little bit of time to talk this over about where we should go next. But before I do that, one of our partners in this endeavor is the Microscopy Society of America, and they have something that the Snap folks don't yet have, which is the leader of the Microscopy Society has the Grand Poobah hat. And I think the Snap community would be enriched if our leaders also were required to wear a Grand Poobah hat so that everyone will know who they are at gatherings like this. In a more serious vein, Louisa Marchesa is a research scientist at the university, at Ohio State University. She studies heart disease and including atrial fibrillation. Since I've had that particular disease, I'm all in favor of people. She's been able to use microscopy to develop a therapy that she's patented. And I approve of that because I like it when scientific researchers find therapies for issues that I either have or may encounter. But she also leads Project Micro, which is their outreach program. So far, they've done materials that they've distributed and have been used by more than 10,000 teachers. And we're hoping to distribute the SNAP microscope through the Microscopy Society of America. So if we can go back, I think that you can stop sharing the screen.
On our page.
Oh, I'm sorry. And also, we put up a couple of materials. We put up a link to an article about this that was published in this month's issue of Technology and Engineering Educator. You want to quickly go there? And so if you're interested, you can download the article that tells about this in more detail. And we also have a link, if you want to go to the other link, to the CAD library, which is a library that we developed where people can post CAD models for schools. And you can download the 3D printer files and the teacher resources and print one out for yourself. So I think we can stop screen sharing and just move us back to the other screen if you would. And so, okay. Very good. There's a YouTube, I'm not sure what that is, but we'll look at it later. So I think that's what we wanted to tell you. I'm not sure where we are with time, but I was hoping we'd have a moment or two for our thoughts because we are eager to get your input on where. I also just want to particularly thank Bernard and all of his comrades for developing the languages that allow us to use the microbit to make a computer controlled microscope. Let me just, I'm gonna give you a, oh, can you? Okay. All right. Well, we'll give you a closer look. And then what you'll see is we've got a second monitor. One of the things I mentioned is that we use Legos because everybody loves Legos. And so the minute they see Legos, the prototyping, this was prototyped in collaboration with middle school and high school students, both in the US and in other countries. And if you can see, there's a stepper motor that's controlled by a motor controller. And then MicroBlocks does all the focusing, and then snap is where you display the image once it comes into focus and capture images and so on. But it's amazing. Almost anything you can think of in the snap community, there's somebody that will, no matter how esoteric, there's somebody that knows about it. So can we go back then? Or are we still showing?
Yeah, there it is.
Okay, comments, thoughts?
Thank you, Glenn. This was like, once again, you're showing kind of the most awesome things like that combine just everything, like graphic effects and manufacturing and optics and research. Wow. This is amazing. And you only see this at SnapCon. Okay, good. I think we've got time for a round of questions to all the preceding talks. Like if there's any talk you'd like to ask something or remark something about, let's take a couple of questions.
What's the, sorry, this is a question for Glenn and Joe. What's the augmentation, what do you call that? The amount of augment?
Yeah, so the basic microscope that you just focus by hand with the manual control is up to 100 times. Beyond that, you really need the automated focus to get the jitter out of the stage and that goes up to 400 times. So it's small enough to see things like amoeba and paramecium and small protozoa in water samples.
So what we were seeing on your snap stage was actually
That was an onion skin.
Right, that wasn't a photograph, that was a live view of an onion skin, magnified 400 or 100?
That was at 100.
Yeah, that was an onion skin magnified 100 times.
And the way we're able to do that is we're using the same objective lenses and eyepiece lenses that standard microscopes use.
Most of the lenses, fairly good lenses that are used in school microscopes, cost about $20 a piece. And then the rest of the cost of the and it also turns out in a lot of schools, the microscopes break, but the shipping costs are greater than the cost of the microscope. So these broken microscopes sit in school supply closets. But then if you recover those lenses and 3D print your own microscope, then you can make use of them in schools with scarce resources.
But right now, 400 times is the maximum. We could go a little higher, but we'd have to get a brighter light and probably get into oil immersion.
Yeah, one of our visions is that this will actually be enhanced by the students. So our vision is that the students in the school make microscopes for use in science classes. And we believe that's a good idea, because then if you see whatever you've made being used by somebody, you'll get ideas for enhancements and improvements. And as students in schools around the world post enhancements, we'll add those to the CAD files. And hopefully there will be a continual cycle of improvement. So over time, there will be more and more enhancements. At least that's our hope.
Oh, that's off.
But as
Other questions? Anybody's online having questions? Oh,
Okay, Ryan has a question.
Brian has a question.
Unsurprisingly, this is great stuff. My question is about kind of a side issue that you brought up in passing when you talked about that other 3D printed microscope and said what a shame it was that the innards are covered, so you can't see how it works.
yeah.
Now, when something is run by a computer, my question is, how much can you actually see of how it works, even if it's not covered? I mean,
Well,
about?
when I first started working, we're a somewhat similar era. And back in 1975, we had an Intel, the chair of engineering at Parrish agreed to have a seminar where they made a computer for the School of Education. And it had 4K of memory, used an Intel 8080 processor. And we programmed in assembly language because we got on the HP timeshare system and we downloaded the code and punched it out on paper tape. And then we did a bootloader where we used the paper tape to load the program into that computer. And then when we did a translation to higher level languages, as the computers got more memory, Dan and Molly Watt did a workshop on logo, and we learned that the TI 99/4 computer would run logo. And so, but a lot of people said that like handcrafted candies, assembler was better. It was more efficient and you really understood what's going on. And my sense of it, speaking as somebody who doesn't have any degrees in computer science or computer engineering or any, but just has been lucky enough to participate in this as it's unfolded over the years. I think that it's like an onion and there's always another layer. And in my experience, science teachers feel that you should always in science classes get to that bed layer of truth. But my belief is you never get, there's always another level. And so it's more a question of how deep can you go. In my case, the layer that I want the kids to be able to do is take something like the Gaussian filter in the Snap Pixels library and play around and make changes and see how it works. So to that extent, now, you know, what's happening on the microbit, to be honest, I don't have the slightest clue of what's on the chip. I know that in MicroBlocks, when you look at the pin 8, say, if you don't click the thing that says pull down resistor, then the voltage floats between 0 and 3.3 volts, and you may get an indeterminate result. But how the pull down resistor option works or what happens inside the microbit, I don't have a clue. So I think it's like at what level of abstraction. And I think what I think is important is for the kids to be able themselves to make changes and see a difference and then come up with their own inventions. But pedagogically, I think that's one of the most interesting things. At some point, you always have to work with an abstraction. It's just what layer of abstraction are you at? That's just my sense of it. I would defer to you just got the award for teaching, so I would defer to your pedagogical expertise. What do you think?
I mean, I was wondering about what can you actually see inside the microscope that gives you insight into how it works.
Oh, okay. Well, let me give you a great example. And so this is the focus mechanism right here, okay? And so when we first started, and what you would typically find in a school microscope is a planetary gear. So we decided to do a bevel here because it's easier to understand how it works. And what we found was when we added the fine focus knob in the bevel gear, the coarse focus no longer worked.
Yes, I think you.
And then we realized, oh, you need a helical gear, not a straight gear. The curved helical gears lets the coarse focus and the fine focus. So that's the sort of detail you can see. Or another thing, if you look inside the barrel, now I'm embarrassed to say how many months this took us, but we were getting beautiful views of the inside of the barrel with the USB camera instead of the slide. And we, with help from the folks at the University of Edinburgh, we realized we need to put baffles in to absorb the light so that the camera can focus on the slide. And this was something that we were ourselves baffled by, pun intended, for months.